All right, so continuing with structures and properties of matter, topic 1, Introduction to Matter, lesson 3, changes in matter, found on pages 24 to 35 in your textbook. So changes in matter. First, we need to circle at least 2 things in the photo that are undergoing the process of changing matter. So one thing would be the marshmallows, and another would be the wood. What is causing the marshmallows to change their state of matter? The heat from the fire. And why do you think matter changes state when outside forces act upon it? And outside forces cause the molecules in matter to either speed up or slow down, which might cause the molecules to rearrange and result in changes in physical properties. Physical change. Physical change alters the form or appearance of matter, but does not turn any substance in the matter into a different substance. So breaking glass, carving wood, bending metal, crushing a can. It's all still the same thing. So you break glass, it's a different shape, but it's still glass. You carve wood, it's a different shape, still wood. Changes of state, solid, liquid, gas, those are physical changes. We're not changing the substance itself. So water freezes, it's ice. Ice is still water, it's solid water. If something dissolves in it, it is not. So if we have water and we put sugar in it, so sugar water is not a chemical change, it's not changing anything, it's just changing the state of the substance as in its physical state. So again, what happens when water freezes? It turns to solid ice. And when ice melts, it turns to liquid water. What happens when water boils? At that point, it turns to a gas called water vapor. And has the water been changed into a different substance when it freezes, melts, or boils? No, it's still water with the same chemical formula, no matter what state, solid, liquid, or gas. So sculpting ice, an ice sculptor breaks ice and shapes ice, but he or she does not cause it to change into another substance. It's still ice. All right, reading check. How are melting and carving ice sculptures both examples of physical change? So in both cases, water isn't changing into something else. It's either changing state or being broken into smaller pieces, but it's still water, or H2O. Remember that when you write H2O, the 2 is a subscript, meaning that it's a smaller number at the bottom. So a subscript is the opposite of a superscript. So something squared, when you square something or cube something, that's a superscript. A subscript is at the bottom instead of the top. Now for our model it on page 26. So we need to make a paper airplane out of a piece of scrap paper. Draw a sketch of your paper airplane in the space provided. So there's roughly what my paper airplane would look like. What kind of physical changes did you cause to happen to the paper? So there was folding or changing shape. So we folded it, we changed its shape. It's still paper though. How can paper that has already been used be physically changed to make other paper products? So it can be shredded to make pulp, to make new paper, cardboard, and other products. Chemical changes. So a chemical change, on the other hand, is a change in matter that produces one or more new substances, sometimes referred to as a chemical reaction. So when something's on fire, that causes a chemical change. Photosynthesis is a chemical change. Making bread is a chemical change. Iron rusting is also a chemical change. There are different things that show evidence of chemical changes. So this is figure 4 found on page 28. So next to each photo, we need to identify evidence that a new substance is formed. So first we have tarnishing, which is the slow combination of a bright metal, such as silver, with sulfur or another substance, which produces a dark coating on the metal. This is an example of a color change, and that's one of the evidence that a chemical change has occurred. Oxidation is the combination of a substance with oxygen, such as when iron rusts. This is another example of a color change. Oxidation also occurs with apples. That's why when you bite into an apple, the inside, the fleshy part, starts turning brown due to oxidation. That's a chemical change that's occurring, shown by the color change. Objects catch fire when a fuel combines rapidly with oxygen, producing heat, light, and a new substance. So we have flame, a color change, and temperature change. All of those things are different evidence that show that there's been a chemical change. Lastly, bubbles are created by using electricity to break a compound down into elements or simple compounds. So in this example, we have gas bubbles. So the gas bubbles show. Now, that being said, this is different than, so like in this, gas bubbles do show a chemical change. However, when we're talking about like boiling water and water boils, those bubbles are not representative of a chemical change. So we have to be mindful of that because that's just changing from liquid to gas. But these bubbles are formed in the water. So because things are breaking down, right? And that's not necessarily what's happening with water. It's still water. So that is a little confusing. Normally bubbles are a sign of that, but water boiling is not. So just bear that in mind for the future. All right, conservation of mass. So when a piece of paper burns, is this a chemical or physical change? We know that there's fire in there, and therefore it's a chemical change. Does the paper lose mass during this reaction? So you might think that it does because it turns to ash. However, it does not. The mass, which is comprised of atoms, are just rearranged and turned into a different substance. So that to say, if we were to take a piece of paper, a way that we could show that this happens, take a piece of paper, we measure that piece of paper, we mass it, and then we set it on fire, we collect all of the ashes, and then we were to measure the mass of those ashes, they would be equivalent, or roughly equivalent due to some user error, human error. It could be a little off, but this has been proved. Conservation of mass, it will have the same mass. So what can happen to matter during a chemical change that might lead you to think it has disappeared? So the new substance that forms might be invisible or odorless. So this is a good example, sometimes gases. So sometimes we have a chemical change, we light something on fire, and some of it is gone off in smoke, some of it comes out in other gases that form, and those we can't necessarily measure. So that would be another thing. If we took that paper, we burnt it, we took the mass of it, if it was off by a decent amount, we would then assume that some of it went off in gas form. So how does the law of conservation of mass account for these types of changes? So the new substances are in different states, or the atoms are arranged differently. So that's another way to say what I just said before that. So the law of conservation of mass states that matter is not created or destroyed during a chemical reaction, but the atoms in matter can be rearranged to make new substances. It's also called the law of conservation of matter. So the law of conservation of mass, law of conservation of matter, same thing. So reading check. Why do you think the conservation of mass pertains more to chemical changes than physical changes? And with physical changes, there's no change to the substance, so its amount necessarily stays the same. And a chemical change, the fact that the total mass remains the same isn't necessarily obvious, like our paper example. So we have the paper, we see it, we light it on fire, we have ash. We don't necessarily intuitively know that the mass of those two things are going to be equivalent. So that's why chemical change is more pertinent in regards to law of conservation of mass. When we have a piece of glass and we break it, we know that it weighs the same because we have the two pieces of glass which are part of the one piece. So it's still the same, nothing's changed. It's just in smaller parts. If we were to take those parts and mass them, it'd be the same. And that's a lot more intuitive. We just know that. So conservation of mass, page 29. So first, let's read this and then we'll go on to do the instructions. So the combustion reaction that produces carbon dioxide and water from methane and oxygen does not result in any gain or loss of mass. All atoms that go into the reaction are present at the end of the reaction. So the first thing we need to do is count the atoms of each element before and after the chemical change. So fill in the numbers in the appropriate boxes. So we're looking for carbon atoms, and there is 1 carbon, hydrogen, counting the H's, 1, 2, 3, 4, and oxygen, counting the O's, 1, 2, 3, 4. So we have 1 carbon, 4 hydrogen, and 4 oxygen. Then on the other side, we're going to look, and we're counting from both sides, so everything together. There is 1 carbon, 1, 2, 3, 4 hydrogens, and 1, 2, 3, 4 oxygen. So again, we have 1, 4, 4. And you'll notice that both sides have the same number of atoms. 1, 4, 4, 1, 4, 4. The next thing we need to do is answer the question, does the ratio of hydrogen and oxygen atoms change during the reaction? Compare the number of atoms before and after the reaction. So I just stated the answer to this. No. Initially, there are 4 hydrogen atoms and 4 oxygen atoms. The same is true at the end of the reaction. The atoms just rearranged to form different substances. But the overall mass was the same before and after the reaction. Conservation of mass, page 29, last section. Antoine Lavoisier was able to show that mass wasn't lost or gained during chemical reactions by weighing all of the matter in the system before and after reactions occurred. What questions would you ask Lavoisier about how he conducted this investigation? So one good question that you could ask is, how did you measure the mass of substances that are hard to measure, such as gases? That would be a very good question. If you have another question that you would ask, feel free to write that down there. All right, energy transfer. How does energy transfer exactly? Moving molecules have kinetic energy. Which particle has the most kinetic energy and the least? So particle A is going to have the most kinetic energy, and particle B would have the least. When particles collide, kinetic energy is transferred. Energy can be transferred to make things warmer or make things cooler. The transfer of energy causes phase changes in substance. For example, an ice cube melting or liquid water freezing into a solid. But how does energy transfer? So we have particle collision, a good example of one example of energy transfer. So a fast-moving particle A and a slow-moving particle B are on the collision course. At the moment of impact, energy transfers from particle A to particle B. The two particles now move at about the same speed. So we have one moving faster than the other. They collide. After they collide, they move away again, but now they're going the same speed because all of that energy came together and then was separated equally. So again, how does energy transfer? Temperature, a measure of the average kinetic energy of all the atoms or molecules of a substance. Heat, energy always transfers from a substance at a higher temperature to a substance at a lower temperature due to particle collisions. Energy is always transferred from the faster moving atoms to slower moving atoms. You can make something colder only by allowing its energy to be transferred to something colder. Energy will transfer until the system is in equilibrium and the temperature in the system is constant. Which cup shows equilibrium? So the 10 degrees Celsius water is going to be at equilibrium. because in the 100 degrees Celsius water with the 0 degrees Celsius ice cube, the transfer of energy is still going. It's not at equilibrium, it's still moving. And then it stops once the ice all melts and everything then gets to 10 degrees Celsius and it's all equal. So energy transfers from particles in the hot water to particles in the ice. Energy and matter are related. Like matter, energy is never created or destroyed. It is only transformed. Again, temperature is a measure of how hot or cold something is and is related to the motion and energy of the particles in matter. Warm means that there's more energy and cool means that there's less energy. Thermal energy is the total energy of the motion of all the particles in an object. It's important to remember that energy flows from warm matter to cool matter. So, low movement means that you're going to have a low temperature. High movement means that you're going to have a high temperature. So, movement of thermal energy in practice. So, this is figure 5. A polar bear swims in very cold, frigid water in the Arctic. Draw an arrow in your textbook to indicate the direction thermal energy moves in this image. So, the energy is moving from the polar bear into the water because the polar bear is warmer, the water is cooler. So, it goes from warmer to cooler from the polar bear to the water. And this one, people are relaxing in a warm geothermal pool in Iceland. Draw an arrow in your textbook to indicate the direction the thermal energy moves in this image. So in this case, the pool is warmer, so it is moving to the person. So it goes from the water to the person because the temperature of the water is warm. Literacy connection. How can you use terms such as thermal energy, particles, motion, and flow to explain the movement of heat in our world? So heat is thermal energy that is transferred when heat flows from one object to another. The motion of the particles in the second object will then increase. Energy and matter are related. When matter changes, the thermal energy is usually released or absorbed. Endothermic is when thermal energy is absorbed, and exothermic is when thermal energy is released. So chemical energy is energy that is stored in the chemical bonds between atoms of any substance. So ice melting, that is endothermic reaction because it is colder than its surroundings. Fire is exothermic because the exothermic reaction is hotter than the surroundings. Energy is conserved in chemical reactions, and the total energy of the system is the same as before and after. So why does ice melt? Ice absorbs thermal energy from its surroundings, leaving the air around it feeling cold. Is this endothermic or exothermic? And as we just talked, that one is an endothermic reaction. Sorry, I moved a little bit ahead of time. So how is chemical energy in your food transformed? Energy from food changes into energy used for organs and muscles to function. Burning the food fuel transforms the chemical energy in our body and releases some energy as heat, the form of increase in the body temperature. Is this endothermic or exothermic? And because heat is released, it is exothermic. Energy and chemical reactions, page 31. A student starts 2 chemical reactions by adding a different substance to each of 2 beakers with different solutions. She observes them for 10 minutes, recording the temperature of the solution in each beaker every minute. The beginning temperature for both solutions is 22 degrees Celsius. What was the temperature changes of each solution after 10 minutes? So Beaker A got 28 degrees Celsius warmer, and Beaker B got 17 degrees Celsius cooler. Which of the beakers had an endothermic reaction and exothermic reaction? So reaction A was exothermic because it got heated, and reaction B was endothermic because it got cooler. Which solution could be used in a cooling pack to keep food and drinks cold in a cooler? Explain. So the new solution in beaker B would be better because it would draw in thermal energy from its surroundings, including the air in a cooler and any food and drink in contact with the pack or the air. All right, so our lesson check. A large bar of solid gold is melted into liquid. The liquid is then poured into molds to make a number of gold coins. Was this a chemical or physical change? Explain. It's of course a physical change, because changes of state and shape are not chemical changes. Gold did not change into something else. It's still gold. If you cut an apple into slices and leave them in the open air, they will slowly turn brown. What kind of chemical change is this? Explain. This is oxidation. If you'll remember, I talked about it specifically in our notes. Substances in the apple are reacting with oxygen gas to produce new substances. A friend notices that a nail that was left outside for a few months seems larger and heavier than it was before. He says it disproves the law of conservation of mass. Explain why he is wrong. So some of the added mass on the nail is from oxygen gas, which was in the system but was not accounted for because it's invisible. 4. A northern right whale migrates from warm waters off Florida to cooler waters off Nova Scotia. In which area do you think more thermal energy would move from the whale to its environment? Explain. Off Canada. Thermal energy probably flows from the whale to its environment at all times, but more so when its environment gets colder. A stick of butter is melted in a saucepan. As it continues to cook, the butter turns brown. What changes have occurred to the butter? The melting of the butter was a physical change. It was still butter at that point. As it continued to receive more thermal energy, substances in the butter began to burn. This was then a chemical change. And that ends lesson 3 as well as this topic.